Mr. Hefner here, and here is a video on uniform and non-uniform force fields. There's an example of the Earth's magnetic force field here protecting us. We've got the Van Allen belts capturing a lot of the ion radiation from the sun, which allows our technology to thrive and keeps us from getting horrible, horrible amounts of cancer. So, force fields. They are regions where fundamental forces of the universe have observable effects. They are gravitational, electro-magnetic, or nuclear. And in the region of the force field, it can be fairly constant, and then we call it uniform. Or it can vary a great deal of position. We call that non-uniform, and we also call that a point source, because you can pretend that the force field is originating at an infinitesimally small point inside the object that the force field is coming from. So, the force fields, we got gravitational, electromagnetic, which is electric and magnetic, and we got nuclear. We're not going to look at nuclear in this course, it's just beyond the scope of our course. And then we got the two flavors. We got the uniform, where the lines are all parallel like this, and the force field strength is the same everywhere within the region. Or we got non-uniform, where the field lines meet at a point, and it's a little misleading, this diagram. The force field is usually from the surface of the object and out. There is some inside, but I mean, you'd have to dig in, which is kind of silly. So force fields are not really like the ones you see in sci-fi, like this, or like this, okay? It's not quite like that. All right, so a uniform gravity field, or G field. So the surface of a planet has a fairly constant gravity field. So if you're walking around on the planet Earth, the force of gravity, the strength of G, the acceleration of gravity, it's pretty consistent for you. It's not going to change or vary that much. And even if you climb a tall building, you can see that the Earth is fairly flat in your area. Like to see the curvature of the Earth, you have to be able to go pretty high. So the mass of the Earth is 5.98 times 10 to the 24 kilograms, and the radius of the Earth is 6,380 kilometers, or 6.38 million meters. Find G. So you can find G because the simple gravity formula and the universal formula should give you the same values when you're on the surface. So if you're standing here, it shouldn't matter which formula you pick. So if we set them equal to each other, we get a value for G. To calculate G on a planet, it's just big G, the constant of the universe right here, times the mass of your planet divided by the radius of your planet squared. And we get negative 9.8 newtons per kilo, or meters per second squared. So if you're on a portion of the Earth, or people may be playing baseball near a tower, a cloud, whatever, you're going to find the acceleration due to gravity and the force field strength G are around 9.8. It's funny, if you change the gravitational constant in the universe just a little bit, then the universe would not have stars and it wouldn't have any life. Just like a 5% difference, supposedly. Okay, so once you've found G, you can just double check that yes, using F equals ma, mg equals ma, that your acceleration is equal to G. And that only happens for gravitational force fields. And it has to be a nice uniform force field like this. Okay, a non-uniform force field. So in this case here, the G field, the gravity field, the acceleration due to gravity, the force field strength G, the force of gravity, they're going to change with location. So for example, let's find the G value at different altitudes of 638 kilometers, which is 1/10 of an Earth radius, 12,760 kilometers, which is 2 Earth radii, and let's say we still know the Earth's mass and we know the Earth's radius. So number one, this person here is only at a altitude of 638 kilometers, still higher than the space station, which is around 408. What's the G value there? So if you could climb a ladder and it's no longer 9.8, what would it be? So the force of gravity at this location is going to be equal to the force of gravity universal. The m's cancel out. Doesn't matter who you are, you get the same force field strength at that point. And we get negative 8.1 newtons per kilo. So just climbing 1/10 of an Earth radius, you drop from 9.8 to 8.1. Now what if you're far away, 2 Earth radii away? Okay, so let's find out what happens then. Oh, sorry, I forgot. I was going to show you, there's another way to do this. You can use proportionality techniques instead. So if g is equal to gm over r squared, then g really only depends on 1 over the radius squared, because g and m aren't changing. You're not going to change the mass of your planet or the gravitational constant of the universe. And so then using something I just call a little Jedi trick, which is ratio proportion math. If you want to find out what one g value is compared to another, so you just go like g1 compared to g0 when you're on the ground, then the new number, the 1, wherever that is, that's going to go where it is in the original fraction. So if I'm looking for g1, then r1's got to be on the bottom, like it is up here. And the original value would be the inverse of that up top. And so we get this negative 9.8, the original g value, 6,380 plus 638 kilometers squared over 6,380 kilometers squared. And we get the same answer. And this is cool. If you use ratio proportion math, you don't even have to switch to scientific units. And you can ignore things like big G and big M. You don't even have to use them all. It saves a lot of work. So now let's take a look at person 2 here. Okay. So person 2, what's going to happen if you're 3 Earth radii away from the center? So you got an altitude of 2 Earth radii, which means you're actually 3 Earth radii away from the center. So you got the radius of the Earth plus the 2 Earth radii. And you get, if you're that far away, if you're at an altitude of 12,760 kilometers, gravity drops all the way down to minus 1.1 newtons per kilo. So that's a huge, huge difference. Okay. But we could have just used ratio and proportion math again, really. Heck, we don't even have to use kilometers or meters here. G equals negative gm over r squared, which means g is depending on 1 over the distance squared. So we just do that little Jedi trick again. G2 equals G0. And then the 2's keep the same location that they did in the original fraction, so R2 squared. The original numbers do the inverse of that. So if R is on the bottom here, then R up top would be the inverted of that, R0 squared. And we get negative 9.8 newtons per kilo times 1 Earth radius squared divided by 3 Earth radius squared, or radii squared. And we get 1/9 of our gravity, negative 1.1. So there you go. So as you can see, that's how it works. All right. So what would G be if you went to 100 Earth radius, right? That's pretty easy. You can find out 1 divided by 100 squared. This is 1/10,000, or 0.000098 newtons per kilo. So at that point, a 100 kilogram person who normally weighs 220 pounds would now only weigh 1/10,000th of that, 0.022 pounds. So you just use ratio proportion math. So easy. Okay, so now let's take a look at electric force fields. So an E field, so we use the symbol epsilon for this. You find those in parallel plates. In parallel plates, in the center region, the force fields are straight lines. Once you get towards the edge, it starts to curve a bit, but for at least 2/3 of the parallel plate, it's a straight one. You see parallel plates in old TV screens. So you got the horizontal and vertical, like the old CRT televisions. And this is one way you can make it very dangerous. Don't do this at home. Do it yourself, parallel plates. A couple pie plates with holes cut out, attached to a car battery, and boom, you got your own particle accelerator. Don't do that. You'll probably electrocute yourself. Very dangerous. So to calculate the force field strength in parallel plates, it's really easy. You just find the voltage, like 12 volts, divided by the plate separation, 0.1. And we get 120 newtons per coulomb. All right, and then once you got the field strength, you can find the acceleration, F equals ma. The force is the electric force, Q epsilon equals ma. So we're going to get 2 times 10 to the negative 6 coulombs on our little pith ball right here inside the parallel plates, which have 120 newtons per coulomb of force field strength. And then we divide by the mass of our pith ball right here, 0.001 kilograms, and we get an acceleration of 0.24 meters per second squared. So pith balls can be made of styrofoam or some other material, something that can hold the charge. It's got to be an insulated material. Right, so here's a non-uniform force field for electric force fields. A Van der Graaf generator is a great example of that. So the brushes inside rub to cause a huge negative electric charge. So you have like negative 70 microcoulombs of charge, providing 400,000 volts to 400,000 volts. And the radius of this Van der Graaf is 12.5 centimeters. Okay, so what if you take this 2 microcoulomb pith ball, which has got 1 gram of mass, and you stick it at locations of 1 meter and 10 meter. So remember, the simple formula has to be equal to the universal formula. So epsilon is equal to kqqq over r squared. Okay, and the q's cancel out. And we get, if you are 1 meter away from this Van der Graaf, the force field strength is pretty strong, 630,000 newtons per coulomb. As you can see, you can use Van der Graafs to make your hair stand up too. Alright, so then now you want to find the acceleration at that location, or you want to find out what's going on. You can do F equals ma, Q equals epsilon ma, and I guess we missed calculating at 10. So to find the strength at 10 meters, it's just a 1 over r squared relationship. So if at 1 meter we're getting 630,000, at 10 meters, 1 over 10 squared, 1/100th of that, that would drop the field strength to 6,300 newtons per coulomb. And so we get an acceleration of 12.6 meters per second squared on the pith ball. Here's an example of just how it works for Van der Graaf. The belt travels up, travels near a metal comb, and it accumulates charge on the Van der Graaf generator. Okay, now we got a uniform magnetic force field. So one place you can find a uniform magnetic force field is inside a solenoid. So inside the center region of a solenoid or an electromagnet. You can also make one by just having 2 bar magnets really close to each other. That's another way of doing it. So in this case here, if you are using a solenoid like this though, the formula for calculating the field strength is the permeability of free space, mu naught, times the number of turns per unit length, times the electric current. So for example, I was looking up an MRI machine, which is used to take pictures of what's inside your body. And one of them advertised that it uses 200 amps current. It's got a 35 centimeter radius. It's 1.4 meters long and has 16,000 turns. So if you plug that number in, the permeability of free space is 4 pi times 10 to the negative 7. We got 16,000 turns over 1.4 meters. We got 200 amps of current. And we get 2.87 Tesla, which is around the 3 Tesla they advertised. That's pretty strong compared to the Earth's magnetic field, which is around 45 microtesla. So that's about 64,000 times the strength of the Earth's magnetic field. Pretty strong. Okay, so now what if we have an electron in there and it's traveling at 100 meters per second? What's the acceleration? So magnetic force on a traveling ion is the charge times the cross product of the velocity and magnetic field vectors. So in this case here, it's at a nice 90-degree angle, so we'll be able to ignore that. So there's the 90 degrees right there. Sine 90 is a 1, so we'll just ignore it. So we get, if you rearrange this, the acceleration is equal to the charge, 1.6 times 10 to the negative 19 coulombs, or 1 elementary charge, 100 meters per second, 2.87 Tesla of magnetic field strength, divided by the mass of an electron, 9.11 times 10 to the negative 31 kilos, and we get a crazy acceleration of 5.04 times 10 to the 13 meters per second squared. Divide that by 9.8, and that poor electron's got 5.1 trillion G's of acceleration. Crazy. Okay, now lastly, a non-uniform magnetic force field. Power lines provide that. So anytime you're near a conducting wire or a power line, it's providing a magnetic force field. Might be one reason why some animals don't like to stay under power lines for too long. Probably affects their internal guidance systems. So the region near the conducting power line, okay, to find out what the magnetic field strength is, it's the permeability to free space, okay, times the current divided by basically the circumference of a circle. The further out you are, the weaker it gets, so 2 pi r. So in this case here, if you're 1 meter away from this power line, what's your, so we're 1 meter away from it, what's the magnetic field strength there? So we have 4 pi times 10 to the negative 7 Tesla meters per amp. So this is the permeability of free space. What does permeability mean? Remember, permeability in a coffee filter means the water gets through, but the coffee grains don't. So it just means how easy is it for things to pass through it. Free space, like space, or air is almost free space, is pretty good. 4 pi times 10 to the negative 7. Other substances, you get a more difficult number to pass through. So we get this number times the 200 amps divided by 2 pi times 1 meter. Now this is convenient. 4 pi divided by 2 pi is just 2. So we can cancel out some pi's here. And we get the magnetic field strength near this power line is 0.000040 Tesla, or 40 microtesla, which falls right in the range of the Earth's magnetic field. The Earth's magnetic field fluctuates anywhere from 30 microtesla to 60, averaging around 45. So if you're an animal using magnetic fields to navigate, yeah, this would probably confuse you a little bit. So now we want to find out what happens to this electron moving at 100 meters per second, heading east. Also notice here, if you're trying to draw three-dimensionally, sometimes it's easier not to. X means going into the paper, and O means coming out. So in this case, we get up, down, east, forward, west, reverse. Coming out of the paper or the page is south, and going in would be north or left. So to find the acceleration, use the magnetic force again, QVB sine theta. And so we got one elementary charge, or 1.6 times 10 to the negative 19, the 100 meters per second, the 40 microtesla, or 40 times 10 to the negative 6, sine 90 over the mass of an electron, 9.11 times 10 to the negative 31. And so that electron is going to experience an acceleration of 7.03 times 10 to the 9 meters per second squared, which is quite a bit. So in summary, there's lots of different kinds of force fields: nuclear, electric, magnetic, and gravity. We only look at gravity, magnetic, and electric. And we got two flavors. They can be parallel lines, which is a uniform field, or they can be non-uniform point source fields. So for example, here's a parallel gravity field, or a uniform gravity field. Here's a uniform electric field. Here's a uniform magnetic field. Here's a real point source or non-uniform gravity field. And that's what the relativity version of it is. Here's a non-uniform electric force field. It's stronger when you get close. It's weaker as you move away. You can indicate that by using color coding like I did, and line thickness. And we got non-uniform like power lines right there. Supposedly this is a quantum field right here, this picture. Okay, I hope this helps. Sorry that this video is very long.